Hello students, welcome in your nuclear physics class. This lecture is focused to the mass defect, binding energy per nucleon and packing fraction. So first we will discuss about the mass defect. It was found that the mass of the nucleus is less than the sum of the masses of the nucleons which constitute the nucleus. That means if MP is the mass of the proton, MP is mass of proton and Mn is mass of neutron and A is atomic number or total number of nucleons, Nucleons is number of neutrons and protons inside the nucleus, that is nucleons. It's nucleons, N-U-C-L-E-O-N-S, nucleons. And Z is the number of protons, and Z minus A is finally we have number of neutrons, or you can take N as Z minus A, number of neutrons. Then by the definition of mass defect we denote it as delta M. Delta M is equal to the difference of the sum of the masses of nucleons and the rest mass of the nucleus. So the sum of the masses of nucleons is Z number of protons and mass of each proton is MP plus A minus Z Mn. This is the mass of the nucleons which form the nucleus minus rest mass of the nucleus. Let it be capital M, and N denotes the nucleus. Then ZMP plus A minus ZMN minus M nucleus or Mn represents the mass defect. Now we look at the packing fraction. Packing fraction, simply you can say the mass defect per nucleon is the packing fraction, or you can say F is equal to delta M, that is mass defect, divided by number of nucleons, that is mass number A. This is the packing fraction, or you can say the packing fraction is the mass defect per elementary particle contained in the nucleus, and mathematically we can say F is equal to M minus A by A. So this capital M represents the actual mass of an element in atomic mass unit, and A is the mass number, that is number of protons and neutrons in the nucleus. So this is packing fraction. So this comes into picture from the fact that the atomic mass are considered to be whole number, yet they differ from the integer by some small amount. This variation of atomic mass from the whole number is considered to be due to some deviation of the mass of the nucleus from the mass of the constituents of the nucleons or the nucleus, that is protons and the neutrons. So that's why it is defined as the F is equal to M minus A by A, that is the mass defect per elementary particle contained in the nucleus. So now if we plot the packing fraction with the mass number, then we have curve like this. If this is the mass number and along the y-axis we have packing fraction F, and this is the line corresponding to 0 value of F, then the curve is like this. So this represents that the positive value of packing fraction F indicates that the nucleus is less stable, and the negative value of the packing fraction means that the atomic mass of the nucleus is less than the nearest whole number, which will correspond to the some variation of mass into energy during the formation of that nucleus. Negative packing fraction will imply that the nucleus is exponentially stable because we have to supply more energy to break the nucleus into its constituent nucleons, while the positive fraction will indicate the nucleus is less stable. Now we will look at the binding energy. So binding energy is energy equivalence of the mass defect. So we will represent it by capital B, binding energy. So it is represented by capital B is equal to delta M into C square. So delta M is the mass defect, and if we multiply mass with the square of the velocity of light, then it is equivalent to energy. So that is the energy equivalent of mass defect, that is called the binding energy. So binding energy represents the stability of the nucleus. Higher is the binding energy, more stable is the nucleus, and lower is the binding energy, less stable is the nucleus. So we can substitute the value of delta M as ZMP plus A minus ZMN minus Mn into C square. Now if we add the mass of Z number of electrons and subtract the mass of Z number of electrons in this expression, then we have plus A minus ZMN minus Mn plus MZME. So Me represents the mass of the electron. So here it is Z is common, Me plus Mp. So plus A minus ZMN minus Mn plus ZME into C square. So this Me, mass of electron, plus mass of one proton, this is the mass of the hydrogen atom. So I will represent it as ZMH plus A minus ZMN minus, now this is Mn, mass of the nucleus, plus ZME, mass of all the protons, and so this is the total mass of the atom. So I denote it by capital M into C square. So finally this is the binding energy. Now if we are interested to find out the binding energy per nucleon, then we will divide it by A on both sides. Then we have Z by A, A minus Z by A, M by A, if we divide with A on both sides. So finally we have binding energy A is equal to ZMH plus AMN minus ZMN minus, this is Mn plus, so that is the total mass of the atom. So I represent it by capital M, so mc square. So now if we are interested to find out binding energy per electron per nucleon, so B by A, so it is Mn plus Z upon A Mh minus Z upon A Mn minus M by A into C square. So Mn is the mass of the neutron, and now if we add and subtract 1 on the right hand side, so we have Mn minus Z by A Mn minus Mh minus M by A minus 1 plus 1. We have added and subtracted 1 on the right hand side. So we have Mn minus 1 minus Z by A, Mn minus Mh. So this is minus common, M minus A upon A into C square. So this M minus A upon A is the packing fraction F. So we have Mn minus 1 minus Z by A, Mn minus Mh minus F into C square. So finally we have binding energy per nucleon in terms of the packing fraction. So this gives the binding energy per nucleon. Now if we plot the binding energy per nucleon against the mass number A, then the graph is like, from the experimental data, graph is like this. It initially increases and then there are few spikes, and then it increases and slowly decreases, and it is least for uranium 235. So in this region it is maximum for iron Fe, and these spikes corresponding to the some particular nuclei, and these spikes indicate something important. So from this is the binding energy per nucleon plotted against the mass number A. So this curve indicates that the binding energy of the lighter nuclei like hydrogen or helium is smaller or lower. Hydrogen, helium, like these elements, binding energy per nucleon is lower, and for mass ranging from 2 to 20, there are some sharp peaks as shown in the graph corresponding to boron, carbon, He4 and neon Na20. These spikes indicate that these particular nuclei are more stable in comparison to their neighboring ones. That means they are more stable in comparison to their neighboring ones. So these peaks gives something interesting, and then the curve has a broad maximum, and this maximum is corresponding to the value of 8.5 MeV per nucleon in the range of 40 to 120 mass number, and this is maximum for iron, which is corresponding to 8.8 MeV. This is 40 to in the region of 120, where the range is 8.5 electron volt, and this is maximum corresponding to iron is 8.8 MeV in units MeV. And as the mass number A increases from 120, then the binding energy per nucleon again starts decreases, and it is least for uranium 235, which is 7.6 MeV. So this curve indicates that the lighter nuclei have small binding energy per nucleon, and heavier nuclei have small binding energy per nucleon. That means light and heavy nuclei are less stable than the middle ones. In order to attain the high value of binding energy per nucleon, the heavier nuclei may split into the lighter nuclei by the process of nuclear fission, and the lighter nuclei may unite together to form a heavy nuclei in the process of fusion. So in both these nuclear reactions, large amount of energy is released. So in the next lecture we will discuss about these spikes in the curve corresponding to Ha4, Ve, carbon and neon 20. So thank you for watching.